We have learned that concentrations do affect spontaneity by adding a lot of products, and if you can think of it as Le Chatelier, that can change spontaneity. The equation that we have seen is this one. My Q didn't look very good. So when you have a very large Q, so the larger the Q, that means that you have a lot of products. Well, if Q is very large, you have a lot of products by Le Chatelier, you would think it's going to go to the reactants. So this means when Q is large, this is very positive. It will make delta G more positive. Therefore, it'll make it less spontaneous. It'll make it to go backwards. The same for if you decrease Q, you will make, it means that you are decreasing the amount of products, therefore the reaction is going to move forward, and that can be exemplified by having a negative delta G. Another way to show whether the reaction is moving forward or backward, depending on the concentration, is by using graphs like the one you can see, in which we just show how the change in Gibbs free energy depends on Q. You could think of when the delta G, or the slope, when delta G is negative, it means that the reaction is going to move forward, and that's because your Q is smaller than K. That is, you do not have enough products. Remember that Q is equal to, it has the same expression as the equilibrium constant. So when Q is smaller than K, you need to make Q larger by increasing the numerator, decreasing the denominator, and you only do that by moving forward. And likewise, when you have Q larger than K, it means you have way too many products. The reaction needs to move to reactants, and that means your delta G will be positive in this case. So the spontaneous process will be going backwards. Okay. At some point, when Q is equal to K, your delta G is 0. You will see also that a more accurate description is, instead of talking about increments, is that or if you will, in terms of Q, the derivative of G versus Q is 0. When you have a minimum, that's the criteria for equilibrium. And so we can talk about the slope. When the slope in this area is negative, you're gonna have a spontaneous reaction moving forward. When the slope is positive, the reaction is going to move towards reactants. Okay, so again, there's two different ways to represent delta G in terms of graphs. One is this one. Remember that we also have this one. Do not confuse the two. It's not the same because in here we have the degree of advancing of the reaction. In here, let's call it X, the reaction coordinate, and here, however, is Q. In other words, this is reactants, this is products, but in here each point of Q has a specific combination of reactants and products. So do not confuse these two representations. So let's see if we can answer these kind of questions. So we have this kind of graph in which, and again, we have labeled this as delta G because otherwise we need to deal with derivatives. But so let's try to identify which one is correct. So it says that the reaction is non-spontaneous at D and E, and when we say non-spontaneous, it means that it's going to move backwards. Okay, and spontaneous means it's going to move forward. So at D and E is non-spontaneous. Well, that's not correct because you have a minimum here, so your delta G is 0. In this case, the slope is negative. It has to move forward. So think of it as, if you will, a ball going down a valley. It's going to stop in the middle. So in this case, the delta G is negative, so at D is spontaneous. So let's see, well, and F is non-spontaneous because your delta G, will be positive. So this is not correct. Spontaneous at D, at equilibrium at E, and non-spontaneous at F. That is correct. Let's see if there's another one that we can see correct. Non-spontaneous at D, Well, no, because at D it's actually going to go forward. That is, it's going to be spontaneous. Equilibrium at E, that's correct. But spontaneous at F, no, that's not correct. Spontaneous at D, E, and F, well, that's not correct either. So you may have noticed then that these kind of graphs, if you see something like that, if you have a delta G versus Q, that is, if your minimum is at low Q, that is, and again, remember that Q is product over reactance. If you have a low Q, it means there's a lot of reactants, there's little products. This, you will, if you have an early minimum, it means you have a a reactant bound reaction. That is, probably your delta G will be positive. On the other hand, if you have something like that, in which the ideal combination in equilibrium, it includes a lot of products, it probably means you have your delta G standard being negative. It typically, when you compare 10 players against 10 players, you actually the reaction is gonna move forward. Hopefully this makes sense. Just keep in mind, on top of being able to manipulate the equations, you must have a qualitative understanding of what these equations are. The take-home message is that by changing the concentrations of reactants and products, one can alter the inherent nature of the reaction when you compare 1 molar against 1 molar. Okay, so this is what actually drives the reaction. The standard one is only when you compare 1 molar of reactants mixed with 1 molar of products.